this video, we'll look at a couple examples of completing the square to solve an equation. Now, there are multiple ways to solve a quadratic equation. Completing the square is just one of them. And really, completing the square is a branch of factoring an equation to solve. If we looked at a special pattern, it's the square of a binomial, this a plus b quantity squared. We could multiply that out by expanding it to be a plus b times a plus b, and using the FOIL method to distribute a times a times b, b squared, we could simplify that ab and ba to be 2ab, and we'd get this trinomial. Now, if you wanted to work backwards from this and factor it, if we wanted to work backwards from a squared plus 2ab plus b squared and factor it, we could see that a plus b times a plus b, we could check it with FOILing, that gives us our a plus b squared. What we're going to call this is that it's a perfect square. This a plus b squared is a perfect square. Now look at what we could do with the square root property of that. Let me work backwards just a little bit here. Erase some of that. Now if I had that this a plus b squared equaled some value, just anything, I could solve this quadratic by doing the square root of both sides. Don't forget, when I use that square root property, I have to do plus or minus the square root of that constant. And the square root of a square, the square and the square root just undo each other because they're inverses. So we get that a plus b is plus or minus the square root of whatever c is. So this is what we're trying to get to, is this easy square root principle to solve a quadratic equation. And the way we're going to get there is we're going to rewrite this thing so it is a perfect square. So let's look at how to do that. So here we have our x squared plus 10x plus 14. The first step for using the completing the square method to solve is I need to isolate the x terms. So that's going to leave the x squared and the 10x on the left, and I'm going to move that 14 over by subtracting 14 from both sides. So I have x squared plus 10x equals negative 14. So again, the first step was to move that 14 over so that I could isolate the x terms. Next, I'm going to think through with this 10. There is remember what I'm trying to do. I'm trying to get this perfect square binomial. Or the square of a binomial. We're trying to rewrite this so that when I factor it, it turns into a perfect square. Well, that is only going to happen if I pick this constant perfectly. And here's how you pick it, so you don't have to guess and check, guess and check, guess and check. I'm going to take this 10, cut it in half to get 5, and then I'm going to take the 5 and square it to get 25. That 25 is the magic number that completes the square. So I can add 25 to the left so that I build the perfect square. And if I do that to one side, in order to keep it an equivalent equation here, I have to add the 25 to the other side also. And now when I factor this x squared plus 10x plus 25, I'm going to get x plus 5 times x plus 5, or in other words, x plus 5 quantity squared. So do you see what we've done? We took our x squared plus 10x, and we found that magic number, the 25, that I could plug in here to make it a perfect square. And do you see when I factored it where that 5 came from? This 5 came from what we started with before we squared it. So in other words, the square root of the 25. Finishing this problem up, we'd have x plus 5 quantity squared equals 25 minus 14, or 11. And if I were to now do the square root of both sides, let me write that just a little bit differently. I'm going to leave myself a little bit of space. The square root, applying the square root property principle, I'm going to add in this next step of taking the square root of both sides. Don't forget, when we use the square root principle, that it's going to be the positive or negative square root of 11. The square of a square root or the square root of a square, they undo each other because they're inverses, so I'm left with x plus 5 equals positive or negative square root 11. Now all that I'll need to do to solve for x is subtract 5 from both sides, and I have it. X equals negative 5 plus or minus the square root of 11. Could we try one more example together? This next example isn't quite as easy because it does have an extra step. To complete the square, we want to get rid of the coefficient of a p squared. So I'm going to have to divide everything through by 4 right from the start, which means I am going to get a fraction. Other than that, I'm just going to follow the same steps that I used in the first example. Now for the second example, it is a little bit different because we have a coefficient of the p squared. So what I'm going to need to do first to use the completing the square method is I'm going to need to divide everything by 4 so that I have a flat p squared with a coefficient of 1. If I divide 4p squared divided by 4, negative 20p divided by 4, 19 divided by 4, it looks a little messier because we have a fraction, but it's very doable, so don't panic at that point. And just follow the same method. We have p squared minus 5p, and I'm going to isolate those two p terms by subtracting the 19/4 from both sides. And now, just like I did on the left, what I'm going to do is look for that magic number, that number that when I add it in here, I get a perfect square. Here's how I get that number. I'm going to take the negative 5 and cut it in half, and then I'm going to square it. Watch out that when we square that, it's going to be positive, right? Because negative 5 times negative 5 is 25. 2 times 2 is 4. So it looks like the magic number that I could add to both sides here is going to be the positive 25 over 4. And I'm going to add that to both sides. Now I could factor this p squared minus 5p plus 25 over 4. Notice that because it's a subtraction, the binomial is going to be a difference, a subtraction. It's p minus, don't even have to think hard because I have it off to the side already, p minus 5 halves. Where did that 5 halves come from? It was this negative 5, the coefficient of p, cut in 2. So we have p minus 5 halves, quantity squared, when I factor that, equals 25 minus 19 is 6, so 6/4. Now, because I see a perfect square here, I'm not going to simplify this. I'm not going to do 6 over 4 is 3 halves. Why? Because I see a perfect square in that denominator. So next, when I do the square root of both sides, to use the square root property, don't forget, when I do the square root of 6 over 4, there's got to be plus or minus. Now watch what happens with the square root property, that it's the square root of 6 over the square root of 4. And do you see now why I left that as the 4 instead of reducing it? Because the square root of 4 is going to be 2. But how do I simplify the square root of a square or the square of the square root? Either way, they're inverse operations, so they undo each other, and I'm left with p minus 5/2 on one side, and that's equal to plus or minus the square root of 6 over the square root of 4. That square root of 4 is just 2, and then when I add 5/2 to both sides, I'd have p equals 5/2. Let me write that on 2 lines. There's no reason to squeeze it in. So add the 5/2 to both sides, plus or minus the square root of 6 over 2. And now I can simplify that because it's a fraction with a common denominator. I get 5 plus or minus the square root of 6 all over 2. Now, let me show you that if you had simplified this to be 3/2, that would have been okay. But when we did the square root of 3 over the square root of 2, so we would have had 5/2 plus or minus the square root of 3 over the square root of 2. I would have had to rationalize that square root of 2. I'd have to get rid of the square root in the denominator. So if you did that, we'd end up multiplying both things by the square root of 2. So we'd have 5 plus or minus square root of 3 times 2 is 6. And this would have been 2, and then the square root of 2 times the square root of 2 is the square root of 4, which is 2. So we would have ended up with the same thing either way. But if you did simplify that fraction, we could have solved it we simplified it from there also. So here's a couple examples of completing the square. I know it's not a really easy process to get used to, but once you are used to it, it is pretty easy to apply. So practice it, and you'll find that it gets easier every time.